Now we should be recording, and again, this is comp 422. Whoop. Back up here. Maybe. Yes, Energy Stack Overflow, schedule. Note a week from today is no class. And input validation. Input validation is important for many SQL injections, several others, and for Overflow. That you just want to make sure that the data you have makes sense. Not only is it a good cybersecurity action, but it's also a very good programming technique, because if you get a value that doesn't make any sense, sometimes a really bad value will cause problems later on in the program, and you'd like to catch them early. It makes it much easier to figure out what's going on and correct the problem if you catch bad input early. Here's an example of validating input. Phone numbers. Phone numbers can be in multiple formats, but there is a limited number of formats for what would be an acceptable phone number, basically 10 numerical digits. Or there might be a dash, there may be parentheses, there might be a space there, maybe some people use periods between them. But I think that's most of the formats I've seen for phone numbers. If you accept those formats, then you're pretty good that you've got a phone number. There are regular expressions that will define this. Those of you who remember taking the theory class as undergraduate, yes, whoever thought it'd be actually useful. It is useful, and you can define a regular expression that works for that. Several numerical inputs have check digits. I'll give a couple examples. ISBN numbers. ISBN numbers are international standard book numbers. They're in the back of all your textbooks and all the books that you might buy, and they identify the book. So each book has one ISBN number, and there's only one ISBN number for a book. So you can, that identifies, because there's a lot of multiple titles out there. So this one identifies it exactly. The ISBN numbers were, I think, 9 or 10 digits. Now they're 13 digits for books. And so they have it. The last digit is a check digit. So here's how they calculate it. They multiply every other digit by 3. And then they add up all the sum. So it's the first digit times 3 times the second digit. For the third digit, plus 3 times the fourth, and so on. So here's an example. We have a ISBN number of our textbook. And you take all the digits except for the last one, and you do that calculation, mod 10. By now, you should be pretty good at this mod function. And then you subtract the result from 10, and it gives you a number between 0 and 10. In this case, it's 2, and that would be the check digit. So if you get any ISBN number, run it through this equation, get a number, and that number is not the same as the last digit in the ISBN number, then there's been an error. Somebody has not inputted the number correctly. And this handles a lot of failures of not only incorrect digits, but misplaced digits. If they, instead of going 1, 2, 3, 4, if you go 1, 4, 3, 2, it figures it out. Credit cards also have a validity check. There's a LUN algorithm that is used to check it. And all the credit cards that I know of use this. In this case, they look at all the digits, whereas the ISBN numbers looked at all but the last digit and came up with an equation that matches the last digit. This one looks at all the digits. It's, again, relatively simple. They start with the 16 or however many digits. A lot of credit cards have 16 digits. You multiply every other digit by 2. Now, if that multiplication produces a number that's over 9, well, okay, 5, 6, 7, 8, 9 produce digits, then you add the values together. So 6 times 2 is 12, so you add it together, you get the value 3. Here's an example for the number we have up here. You multiply them together, and you see over here, we've got 5 times 2 is 10. So 1 and 0 is 1. 7 times 2 is 14. 1 and 5 is 4 is 5, and so forth. So these are you get, again, 16 numbers, add them all up. If the number is evenly divisible by 10, or for those of you who like modular arithmetic, if mod of the sum is 0, then the number is correct. So that's a lot of things. And if you are generating numbers for some purpose, you may want to think of check digits, because a check digit can be done very easily at the point of input. In other words, if you have a web page that's taking in credit card numbers or ISBN numbers or your own numbers, the web page itself, without looking at any database, could do the digit check and see if the user made a likely mistake entering the number. So that's numbers. Get away from numbers and talk about characters. There are multiple characters, all sorts of letters, and they're represented by a number. So like ASCII, and ASCII is the American Standard Character Set for Information Interchange. It's 8 bits, sometimes represented as 7 bits. Early systems used a 7-bit ASCII, and the 8th bit was always 0. But the number 97 in decimal represents the lowercase a. Since there are 8 bits, 2 to the 8th is 256 characters. So you have 256 characters. Unicode is used by Java, I think in Python, other languages, and Unicode has 2 bytes. You can get 16 bits. There are also 32-bit Unicode values that you can get. But Unicode with 2 bytes, since 2 to the 16th, there are 65,000 some different characters. That allows you to have non-English characters. And so we've got different, this is Arabic, Hindi, and Hebrew there. And just, they all say computer science. That's, Google tells me that's the translation of computer science to those languages. It's interesting, by the way, English, of course, and most European languages read left to right. Arabic and Hebrew read right to left. Hindi reads left to right. And when you type these in, you're typing in something in Hebrew, it does go, as you type the first character, it's on the right side of the field, moving to the left. Same thing with Arabic. Okay. But characters and how they appear on the screen are 2 different concepts. The character, again, represents a number. So that certain bit pattern. And again, 65, decimal 65 is a capital letter A. Was it 95 was a lower letter A. That's the character. How it appears is represented by the font. And there are multiple fonts that you can have. So, you can have A, or, you can see all the different, and this curlicue systems, you have bold, you can have italics, all sorts of things you might do with your fonts. Changing the font changes how it appears on the screen, but does not change the value of the letter. If you copy and paste these, right here, if you copy and paste these into something that only accepts plain text like Notepad, it'll appear all as A's. Okay. Get into a minute, talk about checking characters. Okay, integers. Let me spend a few minutes talking about how integers are stored in a computer, or how numbers are stored in a computer, particularly integers. Integers are almost always stored as binary numbers. We have multiple versions of integers. We have int in a computer, and that's typically a 32-bit integer, although it doesn't have to be. There's also longs, which are longer than an int, and shorts, which are shorter than it. Or at least in the C standard, it says shorts are not longer than an int, and longs are not shorter than an int. They could all be the same size. So depends on how big they are. When you type a number on a keyboard, you're typing in characters. The numerical digits on the keyboard are just like all the other characters on the keyboard. So you read them in as characters, and then if the system wants to use them as numbers, it will convert between the character form and the numerical form. Human beings like to use decimal numbers. There's a reason for that. And We learned way back in elementary school that there's positions. The rightmost digit is the ones position, then next to is the tens, then the hundreds and the thousands. It goes up, each digit being multiplied by 10. It is a base 10 system. Binary numbers are base 2. In base 2, the rightmost digit is the ones, and then the twos digit, which is 2 times that, then the fours and the eights, the six. It goes up, each place is multiplied 2 times the previous place. And so here we have 19 in base 10 or decimal. That would be 11001 backwards of it. It has 116, no eights, after you take the 16, no eights, no fours, and then a 2 and a 1. And so it would be 010011 in 6-digit binary. So most computer systems store positive numbers very simply as a binary number. Ints, longs, characters, bytes, integers, or shorts, they're all binary numbers. When you get to negative numbers, there are multiple ways to represent negative numbers. There's ones complement. Ones complement is very simple. It just inverts the bits. Every one becomes zero, every zero becomes one. That's ones complement. It has the strange fact that becomes a negative zero and a positive zero. I've used computers that used ones complement, and that negative zero, positive zero does become an issue every now and again. Two's complement doesn't do that. Two's complement flips all the bits and adds one. So here are the 8 possible combinations of 3 bits. And as you can see, if the leftmost bit is 0, then it's positive. The leftmost bit is the sign bit. And by generally, it's 0 means positive, 1 means negative. There is a standard for two's complement numbers that we'll not worry about. But here are the values for a 3-bit. Again, you can see that jump goes 0, 1, 2, 3, and then the pattern, it starts with a 1, which makes it negative, is 4, 3, 2, 1. To convert between them, it's pretty simple. You to take a positive number, make it so if you want, say you have a positive number and you want to make it negative, you write it out in binary, flip all the bits, change all the ones, zeros, zeros to ones, and then add 1. And that'll give you the negative number. Same process for converting back. If you have a negative number in binary, you want to figure out what is it in positive numbers, you simply flip all the bits and add 1. It works. Here's some examples. We want to see what negative 3 is. So we're using 4-bit numbers just because it's easy to look at. And you can use 32-bit numbers, but it's stretched across the screen. Okay. Since it's a 3-bit number, remember that the leftmost bit is the sign bit. So here's positive 3. Flip all the bits. Instead of being 0011, it becomes 1100. And then add 1. So it's 1101. And 1101 is a negative 3 in two's complement numbers. Okay. So we want to know what 1010 is. Well, we know it's a negative number. So we flip all the bits, and then we add 1, and it becomes 1100, and that is a 6. After taking the quiz, particularly those of you who took it so fast, you got scores in the thousands, you should be able to do that very quickly. That's negative 6. Okay, figure out this one. First clicker question of the day. There you go. You should see it online. All right. Anybody need a, okay. Just a moment. You need a card? Oh, okay. Heads up. They don't have to be able to see it. You need proper orientation. After the card, put it with the proper side, proper answer on top. Okay, got it. Oh, well, we have here in class, we have two A's, one B, one C, and two D's. That's not very definitive. Folks online are more definitive. They got half the people answered D, which is good because, in fact, D is the correct answer. Let's look at this. I should have written it down, but I won't. 1001. Okay, let's flip all the bits and it becomes 110. Add 1 becomes 111. 111 is 7. Should know that one by now. So it's -7. You know it's negative because it starts with a 1 on a 4-bit value. That's the sign bit. All right. Good enough with that. Everybody got these silly numbers? They'll become important in a minute. All right, here, so arithmetic. If you're doing 2's complement arithmetic, it works the same way for positive and negative numbers. Don't worry about it at all. So here's positive numbers. We'll just add these up. 1 to 0 is a 1. 1 to 1 is 0, 1. 0, carry the 1. So that 1 plus the 1 is 0, carry the 1, 1. Everybody good with that? All right. Here it is. For these, there's a negative number, which, by the way, if you wanted to subtract, you just have to take the second number, convert it to negative, and then add it. But 0, 0, 0, 0, 0. Then 1 to 0 is a 1. 0 to 1 is a 1. 1 to 1 is a 0, carry the 1. 1, 1, 1 is 3. 1, carry the 1. 1 to 1 is 0. So this was 104, negative 16, because 88. And this, in fact, is 88. You can see it's a positive number because don't worry about any carry out. And in this case, it was a 1 carries with 0, 1. The 1 carrying out of the sign place is lost, falls from the bit bucket, and we don't worry about it. Okay, good with that. Now, let's take a look at this one. We have a positive 6 and a positive 3. We're going to add them together. So 0 to 1 is 1. 1 to 1 is 0, carry the 1. 1 to 1 is 0, carry the 1, 1, 1, 1. So that's 1, 0, 0, 1, which from the previous question, we know that's a -7. So we've had two positive numbers, adding them together, and you get a negative number. Most mathematicians don't like that. That's not how I was taught in first grade. Now, if you add two positive numbers, you're going to get a positive number. But because it overflowed, because addition carried into the sign bit, the number became negative. Numbers can only have so many bits and only hold so many values. Here is the range of numbers. If you have a int, it ranges from about -2 billion to +2 billion, plus 2.14. But what's important to remember is a little bit over about 2.14 billion. That's good enough. Bytes or characters, one 8-bit value, goes from -128 to +127. You'll notice in all the examples that there's one more negative number than there is positive numbers. Like 128 to 127. That's because if you, like in 1 byte, 8 bits is 256 values. You're going to split them positive, negative, but you have a 0. Oh, 0 might be positive. So there's always one more negative number than positive numbers. Here's shorts go to 32 and I just remember 32,500. And ints longs go to a really big number. I don't know what that is, but it's really big. Now, in some languages, such as C and C++, not Java, they allow unsigned numbers. Unsigned numbers do not use the leftmost bit as a signed bit. They use all the bits as a binary number. Might point out that your hardware, your Intel processors, your AMD processors, ARM processors all support the concept of unsigned numbers. So if you have unsigned byte or unsigned char, it's 8 bits long, and it goes instead of a signed, it goes from -120. This one just goes from 0 to 255. Shorts 0 to 65,000, and so forth. You get 4 billion up there, 4.25 billion with in a really big number with long. Okay. Now, so what? Let's take a look at this simple little program. We start off, we set a Boolean to false. Then we read in a number, it's an integer, and we go, well, we want to make sure that if cow plus 5 is less than 12. So we say, if cow plus 5 is less than 12. No problem with that. That would work perfectly well. And if it is, you said, okay, to true. But will it always work? What if the user enters a really, really big number? This, in fact, is the largest value you can have for a 32-bit positive integer number. And you add 5 to that. So here is 2,147,483,647 written in binary, all ones. And then you add 5 to it. And it goes forth. And it carries a 1 into the sign bit. So now the number is negative. So if you wrote this and somebody entered the great big number, then this would be true because cow plus 5 would become a negative number, a very large negative number. And so that would count as true, even though this is a positive number. If you had done some algebra beforehand, instead of saying cow plus 5 is less than 12, just say cow is less than 7, then it would work out correctly. This would be false because the great big number, of course, would be less than 7. That is a possible security problem. If you are reading in a number and then checking to make sure that it fits in the prescribed size, if you need numbers that go from 1 to 10, let's say, and somebody enters a great big number, it might not work. So that is an integer overflow exploit. You can also have problems with unsigned numbers. Here, unsigned number, we have a unsigned short. This is easier. You just start with a great big value, add, in this case, I added 2 to it, print it out. What do you get? Well, you get a 1. Because that great big value is all 1 bits. You add number to it, and then this 1 is actually, this is 16 bits. This is the 17th bit. Again, it flows off the end into the bit bucket, and so it becomes a negative number. Or it becomes a, oh, excuse me, never, because this unsigned doesn't become negative, it becomes 1. So that bit falls off the end, and then it becomes 1. So, excuse me? Actually, that wouldn't be there. I probably shouldn't have. There are 16 bits. This is the 17th bit, if you count carefully. I put it there to indicate that it overflows, but that, in fact, would be lost. And so you end up with, anytime you have mod, it's actually anytime you have a unsigned number, it's always mod the maximum value. So this becomes 1. So you need to avoid these problems because this is an exploit that somebody can use to attack a program, takes in numerical values. You can always use longs. Now there is a maximum long value, but the maximum long value is pretty big. Sometimes you can read in an int and then convert it to a long, just copy it to a long, and you won't have to worry about it overflowing. And then if fractions are okay, you can always use doubles. Doubles go up to a very large number, and of course, not quite as accurate. Well, the 64 bits accurate. That's pretty accurate. But some of the number represents the exponent, and some of it the mantissa. So the doubles don't have to worry about overflow. So here's some guidelines for validating things. If you're doing characters, if you're checking character validity, change all your characters to the same character set. If you're using Unicode and you have some ASCII characters, well, either convert the Unicode to ASCII or the ASCII to Unicode, and then check the characters. Don't mix them up. And again, check all the data before processing it. Check it on input. That allows you to respond quickly to a bad input and avoid problems that might occur much later on in the program. And again, anytime you get bad input, reject it, ask the user for something else, or take some action. Don't just continue. You want to validate the range, check numbers to see if they're in the valid range. Check the length. How many characters did this user enter? Is that reasonable? And if you have check characters or particular formats, you can always check that format. All right, that's integer overflow. Let's talk about buffer overflows. Buffer overflows are a big threat. Sometimes I get security warnings and they contain this phrase: the most severe of these vulnerabilities allows a remote attacker to execute arbitrary code. That means they can run their program on your system. That is a big one. The Morris worm, way back in 1988, was over. Did I talk about the Morris worm earlier? Well, let me tell you about the Morris worm. It was one of the first internet attacks. It did take down the internet way back in November 2nd, 1988. It was a small program, 99 lines, and it relied on several vulnerabilities, including a buffer overthrow threat in the Finger program. Finger is a program on a Unix system that you can use to learn about another user on another system. In other words, you can say, Finger Williams. If it's on this system, it'll tell you, is Williams logged in? Or you can go Finger Williams on a different system and it'll tell you, yes, he's logged in over there. Kind of handy. There was an error in the way the program was coded, and Robert Morris took advantage of that. He was a graduate student at MIT. He claimed that he was only doing this as a test, but it escaped and it went over the whole internet, causing all sorts of systems to crash or networks to get cold. The Morris worm reproduced itself. Each one made another copy of it, and soon there's nothing else going across the network but Morris worms. They caught him. He kind of volunteered. He got 3 years probation, 400 hours of community service, and a $10,000 fine, which would be equivalent to $25,000 in money these days. Okay. I think I mentioned this earlier. You get these national. This is an old one. But you can see several buffer overflow vulnerabilities. Okay. Here is another clicker question for programmers and for others. Let's launch this. There we are. Okay. The red digits are there to highlight the. Okay. Understand an answer? I think about it. Realize there are some non-programmers in the class. Important thing to see is there's 4 characters located for this, and we have a loop that's going to go through it 7 times. All right, what's going to happen? Okay. Okay. Oh, all right. B. B is the most popular answer. Almost everybody answered B. That would be really good, except B is not the right answer. The answer is C. It will, in most cases, silently corrupt data and not generate any kind of error. This is a buffer overflow problem. We've tried to put more characters into the array than will fit. Here's an example. Okay, imagine we have a character field name that's 8 characters long, and there's another variable out there. It's a Boolean. It's only 1 byte, and it's called root privileges. Well, imagine it determines whether you have root privileges. Boolean values are true or false. Typically, at least in C and several other languages, the value, if it's 0, that's false. If it's a non-zero value, any number, it's true. At least that's how it is in C. Okay, so here we have it. And we're going to read in a number, CN into the name. So if you type in Smith, then it's SMITH, and then there's that terminating character, which is not /0, it's a binary 0. Remember, all the characters are different numbers, but a binary 0 is used in C to represent the end of a string. So that works just fine. But let's say you type in Armstrong. Armstrong is 9 characters. That's in there. And now the 9th character flows past the end of the array name and puts it to whatever character happens to be past that. And imagine in our example here, it's the root priv. You've just set root priv to a non-zero value. In other words, root priv was false before this, and now if you read in the name, root priv is true. Probably not the desired effect. So that's buffer overflow. There's also stack overflow. Stack overflow is very similar. Most of your local variables, not all your local variables in a program, are stored on the program stack. I'll show some examples. When you enter a method, it puts some values on the stack and uses the stack space for where it's going to store the local variables. And then when you return and leave the function, that space is released and the variables disappear. So imagine you have an array of 4 characters. And it goes on, but if it's on the stack, then there's many other values, and then eventually you run into the return address, where the function is going to return. When you call a function, it stores the return address in the stack, and if you change that, it will not go back to where it's supposed to go. By the way, there's other stack overflows, not generally a cybersecurity problem, but it can happen. That's when you keep generating more and more stack values. Your stack gets bigger and bigger and bigger and bigger until you run out of space. That happens if you try to allocate very, very large arrays on your stack, or runaway recursion. You have recursion, you keep calling a method which calls the method which calls, it keeps over and over and over until each call putting more values in the stack. It just takes up more space until you run out of stack space. That's not what we're talking about here. That is a problem, but it's not the problem. That's not usually a problem for cybersecurity attacks. Here's sort of a diagram of how the program stored logical values. You have different areas of memory. You have your program instructions. Those are typically read-only, and those are what is executed to run your program. Those are the instructions of your program converted to machine language and stored there. Then you have global data, values that are common to all parts of the program, and they're stored after that. Also, constants are stored there. And then you have the heap and the stack. The heap is where the system allocates dynamically acquired variables. Anytime you go new, if you go new widget, make a new widget object, it finds space for the widget in the heap. The stack is where it puts values when you are calling a method. It puts the return address and the frame pointer and local variables in the stack. At some arbitrary location in memory, and in particular, think of virtual memory, the system has a line, and the values above that is where it stores heap values, and below that is the stack. There's also, of course, defines the maximum stack value. If you look at the minor details of like the Java virtual machine, you'll note that you can specify what you want the maximum stack value to be. Nobody ever pays attention to that, but it's there. That is, you can determine where this line is supposed to be. It's actually randomly chosen. We'll talk about that. And stack values in the Intel, as you put something on top of the stack. So if you take your Comp 280 data structures class and they talk about putting something onto the stack, they often display it as being on top. In the Intel, when you put something onto this top of the stack, it is at a lower address. So the stack grows to lower addresses, or it goes down. Okay. Also, something not particularly related to that is byte ordering. There's big endian and little endian machines. That is how are the bytes interpreted for an integer number? And all the integers, that would be integers, longs, shorts, what order of the bytes. For a big endian machine, it stores, well, this would be big endian, stores the first byte first, and the next, and the next, and the next. For a little endian machine, it stores the rightmost or the least significant byte first, and then the next one, and the next one. The most significant byte is stored after that. So you can see an example, little endian and big endian, same values, they're just in different order. Normally, that doesn't make any difference at all when you're using ints and longs and stuff like that. But if you ever are considering a bunch of characters to be an integer, it makes a big difference. By the way, name little endian and big endian comes from Jonathan Swift's Gulliver's Travels book, where Gulliver there were big endian Lilliputians and little endian Lilliputians. Okay, let's talk about the stack. Let's imagine we have a function here that takes a pointer to a float. The ampersand represents a pointer to a value which is a float. A float, again, is a 32-bit double 32-bit floating point number. A double is a 64-bit floating point number. So you can think of a float as a single. And then we have an integer, regular old 32-bit integer. And inside the variable we'll have, or excuse me, inside the function, we have the local variable cow, which has got 4 characters. So back in the main program, we're going to call the function of have an integer called bass, have a float called carp. Trout contains the address of the variable carp. And then we're going to call the function with trout and bass. Trout now being the address of carp and bass being the value 7. Here's how your stack will look. So you start, we have our little stack pointers, points to the next available location. The first thing it does is it pushes bass. So it pushes the values from right to left. So it pushes the value of bass on there, pushes the value of trout. Now, trout was a pointer containing the address of carp. So it puts the address of carp on there. And then it puts the return address. There's usually a call instruction in most machine language or assembly language, and the call instruction pushes the return address on the stack and jumps to the function. When you get in the function, it will put the frame pointer on the stack. I'm not going to spend much time explaining the frame pointer, but let's just say all the functions that you call, the function A calls function B, calls function C, calls method D, it goes on, each one is on the stack, and the frame pointer points back to the previously called stack or frame on the stack. And then after that, it allocates that space for local variables. In this case, we had 4 characters with cow. So that's what the stack will look like. Now, imagine though, somebody puts more than 4 characters into our cow variable. You'll notice that cow goes up as it's cow 0, cow 1, cow 2, cow 3, cow 4 is the first address of the frame. So if you put more than 4 characters or 3 characters and a terminating character into cow, it's going to flow into the next value in the stack, in this case, the frame pointer. If your program does not check for array bounds, like C or C++ generally do not, if you override that, cow and 8, so this is 0, 1, 2, 3, 4, 5, 6, and 7 are the frame pointer, 8, 9, 10, and 11 are the return addresses, and so forth. So if you store something into cow 8 through 11, it will overwrite the return address. And so if you have a program with cleverly crafted input, the attacker could put input into a value that if you overflow the cow array, where you aren't checking to see if the value goes up, it will overstore the return address. And then your program, when it returns, will not go back to where it came from. It'll go to wherever the attacker wanted it to go. And again, I think this says the same thing. We put values in cow, change the frame pointer, and you can put the return address to whatever you want it to be. You can, if you're really attacking, after that, put binary machine language. That is assembled program. It's the binary values of your assembled program, and put that into the tacking field, and that will be stored in that array. And you can change the return address so that it jumps to that program you just loaded in the stack and then execute that program. So the user can put a program into the data and it will run that program that is not the one. So an example of that right after we answer this question. Now, I suppose evil is an objective term. What would cause the most harm? Okay. Oh, all right. A is a very popular answer. B, let's see, online. Well, online people can see that A was a very popular answer. Nobody online said B, C, and alter data. Well, okay. It all depends. I guess it's subjective. My opinion would be C. Although, oh, excuse me, B, answer B. I said B as in boy, as in binary. Changing the return address, that can cause the program to jump back to a different function. I've done that before. Crashing the program, that's always kind of nasty. Altering data, that's also bad. But loading binary machine language means I can run my program on your computer without you having anything to say about it. My program can do whatever it wants to do. And I kind of think that's probably the most dangerous threat you're going to see, because who knows what my program may do, but it's probably going to do something nasty. Oh. Okay, I have a demonstration of buffer overflow. And you'd be happy to know we're not going to do this as a lab that I have done in past years and asked everybody to do this, because it turns out that people who didn't take the undergraduate architecture class didn't do well in this at all. I used to teach the undergraduate architecture class for about 25 years. And so I thought everybody knew this stuff. It turns out that you don't. Okay, but so we'll just show you an example. Imagine we have a short program. Of course, it's a short input array. The problem is having array inputs that aren't big enough. Okay, input from a file to go into the input. In this case, it's going to be much larger than the input array. The input's going to overwrite the stack, and it's going to have a little bit of machine language. It's going to be put onto the stack. In order to make this work, I do this with Microsoft Visual C++. I have to turn off several protections that Microsoft or other systems generally provide. I might note that when I started doing this assignment years ago, that you didn't have to turn off the checks because they by default weren't on, but now they are. You have to turn off the stack canaries. We'll talk about those. You have to turn off varying position of the stack. You have to turn off execution stable. But if you do all those things, it will work. Okay, here is the big part of the program. This is written in C++. You don't really have to know, but just I'll go over it. We have the input file, the variable that contains the input file object, integer I, and here's the method. We have an unsigned character. That's kind of unimportant. I think it's unimportant that it's unsigned, but we'll go for it. It's 4 characters long, start 620. Notice 3 characters, can't put more than 3 characters because in C or C++, it puts the null character afterwards. So you need 4 spaces to put those. And then we set I to 0. We have a while loop. And while it's not end of file, meaning while there's more characters to read, you will read get C, gets a character from the file, reads the value from the file, puts it into the string, increments the index. So it basically puts the first character in string position 0, and then string position 1 and string position 2, and does this until you run out of input in the file. The main program just opens that file, calls the method, and then at the end prints normal end, if you ever get there. In the attack, this is the input that we put in to attack this program. And you don't have to think this up, but you used to. But okay, we have 4 characters that are whatever's going to go into the string. Then we have the frame pointer. Remember, that's the frame point that points whatever. It doesn't have to be exact, but it works well if it points to where it's supposed to. Then the return address. Where are we going to return? Well, in this case, we're going to point the return address to this next location, C, past the start of this. So when the program returns, it will go to start right here. It'll start the execution of this machine language. This is the opcode or the instruction in machine language that pushes a value on the text. What value? Well, we're going to put the address of text. Where's the text? The text is down here. So this points to 19. Then we do an instruction that's called LEA and assembler. It's load effective address. And basically, it's going to load the effective address of this value, which is the printf statement. Program can find out the printf is used here. You can find out what the address is and put that there. So it's going to load that into the EXC register, one of the many registers your Intel or AMD processors have, and then do a jump to that address. So put some values per falsify the frame pointer, falsify the return address to point to the next line. The address of the text is this text down here. And basically, the program will print out whatever is in here. Used to be assignment, print your name. And that will cause this program, which doesn't print your name, to print your name. How do you prevent this? There are multiple ways to prevent this, and I'll go over these in more detail. Software engineering, avoid bad, dangerous functions. The getC function is not particularly safe. What choice of languages? Compiler tools, we're talking about there are tools, StackGuard and others. Analysis tools, which looks through this. We talked about static program and analyzers last time. Execution prevention and randomized. Let's talk about these. Okay. First of all, programming errors. It was basically a programming error. You should not write a program that goes past the end of the array. That program had an array of 4 characters and it went past it, allowed it, but if you don't allow input to go more than that, you won't have the problem. Many of the older libraries, we see, if you're an old C programmer, string copy and get string, did not check the length of the target. So you could say string copy from this string to that string. It did not check at all to see if the length of the string where you're going to put it, the target where you're going to put the value, was long enough. It just copied it. And if it wasn't long enough, it just went past the end and garbaged up some other variables that were located afterwards. Get string, just read them in until you came to the end, to a null character, and stored them in there. If the buffer wasn't big enough, too bad. You are expected to write good programs. And there's software engineering. This is very important. Good software engineering practice. Code reviews. Have people look at the code. And not just yourself, because people generally are not very good at reviewing their own code. You know what it's supposed to do. If it doesn't really do that, you don't recognize that immediately because you're thinking about what it's supposed to do, not about what it really does. So code reviews, that simple code review is having a colleague read your program and seeing if it looks correct to them. And then test it. We talked about fuzz testing, test it with input that's too long, too short, different values. Look for vulnerabilities. What can happen? Some of the frequent vulnerabilities that you find. Bounds, again, going off the end of an array. Off by one error. Off by one is where you think the array holds. I'll explain that in a minute. Unsafe library functions. That is, again, using some of those libraries that don't check to see if the result is going to fit. Old code, watch out for old code. It like uses Unicode. It was originally meant for ASCII. It's going to be not going to fit. And there are all sorts of far off, but deadly serious things you can think about. Off by one error. So you know an error is serious if it has a name. off by one errors, or where the programmer forgets that if you have a variable like string defined to be 10 characters, that means it will hold 10 characters. The index is not 0 to 10, it's 0 to 9. Because it starts at 0. And then you have to remember that there's always the null character at the end. So you really only can put 8 characters in there, 0 through 8. You have to account for that in your programming. And if you forget, a lot of times you'll see programmers, carefully check, oh, yes, is the number less than 10? Yes, no problem. And it doesn't work. Original C. Now, C++ has better, there are better values for the old C libraries. Not too many people write in C, although there are a lot of small systems, the Internet of Things objects that are still coded in C that you have to watch out for. And again, generally, these are not attacks. These are mistakes the programmer made that provide an opening for an attacker. And again, most of them superseded. There is a safe function for doing this. And in fact, Microsoft Visual C++, which I usually use most of the time, Visual Studio, if you use the unsafe functions, we'll print out warnings telling you, be careful. Was there a question? Okay, stretching for it. Example of an unsafe, cin, arrow, into a character variable. Doesn't matter how big this is. This would normally not have a bracket there, but it'd be into some variable name that's a character, doesn't check, just reads it in. With the alternative versions, cin, where cin is the standard input get and get line, you can specify the maximum size. You can also not specify the maximum size, but for security reasons, you want to specify how many characters you'll accept a maximum. Don't just read until there's nothing else to read. Read until it's maximum, or you run out of characters. Get S, get string. There's no limit. That's dangerous. There's a series of scanf libraries, scanf, fscanf, ss, all of these, and generally they don't do bounds checking unless you specify how big you want to them. So if you use these, there is an option to specify. If you don't specify, it doesn't check. Again, unsafe string copies, string are dangerous. There's str n copy, or n has one more parameter telling you the maximum size you should accept. Same thing from string concatenation, how big. And again, but be careful when you specify the maximum size. Remember that the array will hold generally 2 less characters than you think it does. Watch out for expanding things from one format to another. If you're going from ASCII to Unicode, it must be twice as big because Unicodes are 16-bit characters as opposed to 8-bit characters. If you are doing HTML encoding, numbers will become bigger. Like an HTML encoding, the less than sign, or greater than sign. Okay, greater than sign becomes ampersand GT something. Well, that's 4 characters instead of 1. So the output, if the input had lots of characters that are encoded, generally in HTML encoding, you don't encode safe characters, the letters, the numbers, but punctuation and strange characters are all encoded. And so if there's lots of those, it will become bigger. And here's another question. See if you were awake. It's easy, true or false. How wrong can you be? I'll tell you. And okay, how wrong can you be? There's true and there's false, and half of you said true and half of you said false. All right, that's pretty. In the online people, more people said false. That's good because the answer is, in fact, false. I think I just said that. Yes, CN will go, if you give it 25 characters on your inputs, you type in 25 characters, it'll go right off the end of 8 and flow into what follows afterwards, which may or may not be captured by the program, or may just mess up. Buffer overflow is a really messy problem because it generally doesn't create any error message immediately when you do whatever it takes to cause the error. The error occurs later, and that can become very difficult to debug. There are several languages and language systems that don't allow buffer overflow. Java and C# are two examples. They don't. Java just doesn't allow stack violations. Every time you put a value into a stack or reference an array, every time you put a value into an array, actually C#, not C+, in Java, check to make sure that you are in balance. Not only every time you put something, but every time you reference it. If you're reading a value from an array, it always checks balance. That makes the program run a couple of nanoseconds slower, but it makes it safe. And Java does not allow stack violations. It works very hard to avoid any possible violations in the stack. You can't overflow things. It checks that. There are systems that will catch the simple stack overflows called stack canaries. A stack canary is a value, multiple values placed typically after an array. So you have an array here, and then the stack canary, and then the rest of the stack. If your program very simply puts 0, 1, 2, 3 into this, and then 4, 5, 6, it'll change the stack canary, and then before the program continues, it checks these various stack canaries. Did you overflow the stack canary? If it's typically before returning or sometimes just during execution, it will check stack canary value correct. If it is correct, then it continues on. If it's not correct, it will stop your program, print out an error message, and terminate your program. Some systems produce a random number and they save what the random number is supposed to be. That way, any attacker does not know what the stack canary value is supposed to be. Microsoft always uses the hexadecimal value that is 8 Cs. So you know what it is. Turns out, if you know what it is, on the previous attack we did, it can be done when there are stack canaries. You simply have to put the appropriate CCCCC values in the right place and it'll work. So you're overwriting the stack canary, but you're overwriting it with the same value that was there. Data execution prevention is a hardware feature that helps prevent against these problems. On the example I showed, we loaded a binary machine language onto the stack, and then executed the stack. Data execution prevention prevents the hardware from ever getting an instruction from the stack. It will not fetch an instruction, will not execute any program whose instructions are in the stack. So as soon as you try to execute a stack, it blows up, gets a data execution prevention error, and terminates your program, which of course does crash your program, but it's probably better to crash your program and have it stop than have it execute some arbitrary program that you don't know what it's going to do. And undoubtedly will do something you don't like. Typically, the operating system will set data execution on all parts of the program that are not supposed to contain the instructions. So the instruction segment will allow data execution, but the globals, the stack, and the heap will not allow execution of a program from that location. So our example that we used will not work correctly. It's one of the features they can do to stop it. And again, if you're the programmer, security is all about you. You can write a program that's insecure and put your organization at risk, or you can write secure programs and save the day. Here's a question about those stack canaries. Oh, wait a second. Something's okay. There we go. Okay. Boy, nobody says it sings. Nobody has any imagination. Oh, oh dear. I wonder what I'm supposed to do about this. It's happened before and I don't remember the solution. My mouse is stuck in the screen. I cannot go over and, oh, something magical happened. Okay, it's done. There you can see the result. And the answer is A. It's A, detects changes. Good, most people liked A. Nobody said it's sung. Oh, share results. There we are. Yes. No, stack canary is a prevention, doesn't cause, helps prevent overflows. Variables in some languages are random values when you start, even in some languages like Java, which is pretty clean. Certain variables, when you allocate them, it doesn't bother to zero the memory, just leaves whatever you have. Okay, as I mentioned, random stack locations are used by some systems where that line between the heap and the stack varies. The program randomly picks a number, and that's the point where now, of course, there's a limit, so it gives enough room for the stack. But then it randomly picks a number, so you don't know where the stack is. Every time you run the program, the stack's in a different place. This makes it very difficult if you're writing an attack where you wanted to jump into the stack because you don't know where the stack is anymore. Each time it's executed, the stack is someplace else. So that is a security feature. Here I have some few, these are just Ken Williams rules for programming that help improve security. Just made these up myself. Okay, error functions generally return an error code if something doesn't work in both C and Java. Sometimes Java will throw an exception. You should catch the exception. And if you catch the exception, you should do something, not have an empty catch block. That's really bad. I think I've mentioned before in a different class, graduate students should know better. A graduate student had an empty catch block. The program was blowing off, throwing exceptions, jumping into the catch block, doing nothing because there was nothing in the catch block, and going on, executing with no errors. Students said, oh, it works perfectly, when in fact it didn't work at all. And you should always check it, because always check all errors statuses, because if you don't, errors may be occurring and you don't know them. Now, most errors are not malicious attacks. It's sad to say, but programmers can create all sorts of errors all by themselves, and they don't need attackers, but you offer the opportunity for an attacker. And then whenever you are storing a value like a password or key or something, when you're done using it in memory, overwrite it. Put zeros on top of it or something, a random value. Put something so when the program terminates, those values are not in memory. Because when the program terminates, it leaves these values in memory, the operating system will then allocate that memory to another program when another program runs, and the program can go out and look and see, well, what's in memory when we started? It used to be an attack game we'd play. We'd just have programs that allocate big chunks of memory and go out and look and see what did we find today. So don't do that. You'll note that in several languages, if you want to read in a password, say in Java or in C++, you have a field, like a text field, where you're going to ask the user to read in you're going to read in a name or a value, it will usually return a string. If, though, you're reading in a password, it returns an array of characters. That's because you can overwrite an array of characters. In Java, you cannot overwrite a string. Strings are immutable. They cannot be changed. So if you type in your password as a string, you can't change it. You can't overwrite it. Compiler warnings. If you compile your program and it gives a warning, pay attention to the warning. Don't just ignore it. There's an option in most compilers to say treat warnings as errors. It means that if you get a warning, it won't continue, it won't run the program. Warnings tell you that something's not right. On rare occasions, the compiler is mistaken and thinks you're doing something that's not right. But unless you're really sure that that is okay, always do something to correct warnings. Besides, you will not always be the person who compiles this program. If it's an industrial situation, somebody else is going to run it and they're going to go, why does this program get a warning? And again, check for validity of input. Check to see numbers are the right type, if they're in the right range. If you're expecting a number, are they numerical digits? You have all sorts of checks. And there are all sorts of functions available to check likely values. There are functions to check. Does this look like an email address? Does it look like the phone number? Does it look like a URL? And it will go out and check. Does it? Yeah, it looks something like that. So you can check for the validity of it, and you should. Okay. That's it for today. Any questions about the material? Hearing none, then I'll just quickly, we just covered overthrow threats. On Monday, I'll talk about election security. And let me remind you that Tuesday, November 5th, is the election. You can also early vote now. So if you haven't voted, get out there and early vote. I've already voted. I wish I could stop seeing all the advertisements from political candidates because I've already voted. It doesn't make any difference. But you should get out there and vote. And if you haven't registered, you may register and vote on early voting. You may not register and vote on election day voting. On election day, if you are not previously registered, you're just out of luck. A week from today, is a wellness day, no class on October 30th. And then we'll be talking about malware the next week and denial of service after that. You might note there's different chapters to read in the textbook. It would do you well to read them. We have a guest speaker. It's Katie Clodd. She's the director of IT Enterprise Solutions for Lincoln Financial Group. That's the company downtown. It has the big building with the clock on the top. Tells you the clock, date, and tells you the time, tells you the temperature. That's the LFG group. And she works there. She hires people. She's the director of the organization and frequently interviews people. And she's going to talk about it. It has nothing to do with cybersecurity. But she's going to talk about interviewing. She's done a lot of interviews and will tell you a lot of clues about interviewing. It'd be well worth your time since I know generally you're either seniors or graduate students, both of whom are thinking about getting another job afterwards. And even if you're a certificate student, who knows? You always might find a better job. So you might want to come. And we will, again, that will be right after I talk about election security. I might also mention, I just pulled this advertisement off the bulletin board for coming to class. It reads, the Women in Cybersecurity Student Chapter at A&T, six-figure field of cybersecurity, opportunity, statistics, and careers. And it has the speaker, Miranda Stanfield, who's going to talk on October 24th. That is tomorrow, I believe, at 6 o'clock in Proctor Hall, room 212. And there's also a Zoom. I suppose if you, well, yes, if you go out to mbs-tech.io, it'll have the website and you can find the Zoom information. Or I suppose if you Google up Miranda Stanfield or the six-figure field of cybersecurity, you'll find, I'm guessing the six-figure field refers to money you can get working in cybersecurity. And yes, if you go out and look at the National Bureau of Labor Statistics, cybersecurity people make a lot of money. Why am I not making that much? Well, that's because I'm retired. I don't care. But yes, you might want to look at that. I recommend perhaps attending that. And that's it for today. So see you on Monday. And as soon as I can think of an assignment, you're going to get it.